Hey, what's up, guys? So in this video, let's talk about the affine local. So there's an idea called affine local. So basically, the idea is that we define a skin, right? So in order, and we know that skin has a affine cover. Right? So if you have a affine cover, right, then but there may be different affine cover. So maybe one people have already proved that there are some property in this affine cover, but it's not sure that where the rest affine cover has it. Okay, so there's a powerful tool called affine communication theory, or affine communication lemma. And we will prove this in the next video, and we will show that, and then in the future video we will show that there are many other property which is affine local. Okay, and I think the very good reference that Vakil 5.3. Okay. In this video that we are going to prove the important lemma which is related to proof the affine communication lemma. Okay, so this is lemma. This lemma I think is very interesting and important, so you can play around with it. So basically, you can check Vakil 5.3.1. I will give the proof, but the proof I give will be slightly different from Vakil because I think it's easy to understand. Okay, so the idea is that we have skin, right? And let's say we have U, which is spec A, where it's a subskin of X, and the V is a spec B, is a subskin of X. And we can ask U intersection V, right? So if we draw a graph, we draw, let's say this is U and V, and let's say there's a point P. Okay, so by construction, right, you know that there will be a distinguished open subset. Maybe this is called D of AF, right? And definitely you will have some distinguished open set. Maybe this way, it's called a D of BG. Okay, but so it's not obviously that this P will have some distinguished open set which actually falls into their intersection. Maybe there is a distinguished open set. There always is distinguished open set falls into, right? Because the distinguished open set for A forms the basis, right? So I can say that, oh, I can find some point, some guy which is here, which is DA or something, but I can always find something which is DB or something. So it's not easy to see that one can find some orbital cover which is both, right? Which is both. So, but this theorem will tell you that yes, you can actually find it. Okay, so basically what I'm saying is that for our P belongs to U intersection V, there's a simultaneously, so let's simultaneously distinguish open subskin of spec A and spec B, which covers P. Okay, so given for every P in the U intersection V, you can find a distinguished open subskin of spec A and spec B which cover P. Simply speaking, right, for every P belongs to U intersection V, you can find F in A, you can find a G in B, such that P is covered by D of A of F. And the amazing is D of A of F as a set is the same as D of G in B. Okay, so you can find a guy which simultaneously contain them. I think this is the powerful tool that we will use in a. This is not completely not obvious, right? Okay, so let's dive into proof. Okay, so proof is a little bit tricky. So let's see. Let's still draw this diagram so that we know what we are doing, right? So let's say this is U spec A and B is a spec B, and this is U and V. Let's say take B. Okay, so U intersection V is open, right? Open in U, right? So we know that distinguished open set forms a basis. So there's F, such that P, right, is a DAF distinguished open set, the U intersection V. Okay. And we know that this guy is also skin, right? This guy is a subskin because we know that this is isomorphic to spec of AF. Okay, so I already have this spec of AF, right? So I have P is a spec of AF in B, and then this guy is still open in B. right? So there is a G in B such that the P is falls into D of P of G, or isomorphic to spec BG is a subset of spec AF B. Okay, so it's very happy, right? It's very happy that we already find a D of BG where it's already in the spec AF. Okay, so the problem is that the final problem is that how can is this guy also what distinguish open set in A? So basically, the question is that can I find some element F, right? Maybe it's different from this F in A. Definitely different F prime in A, such that DBG is the same as DAF prime. If I can find this, I prove the results, right? So this is the ultimate goal. Okay, so let's see. How can I write this? Okay, so I remember that in the previous you can check out Harshon. I always forget how to spell it. I think the Harshon like 2. Skin section 2.16a. So there's an exercise that I previously proved. So let me just quickly recall this exercise. So this exercise tells you that if you start from skin X, right, and you can define the skin, you can define an object, you can define XF, where F belongs to the global section of XOX, and XF is the point which is non-vanishing. Okay, so it's basically the X belongs to X, such that right, so you can push F to the stocks, right, such that Fx is do not inside the M of X, right? So M of X is a maximum ideal of this XOX. Recall that XOX is local ring space, so each stocks has a local ring. So it's a maximum, unique maximum ideal. And I think in the previous video, I will post the link below. Oh, sorry, sometimes you will jump. So XF, if I do XF intersection with spec B, so let's say spec B, let's use spec R. Let's say you have some affine subset R. Spec R will be the D of F bar of R. Okay, so F bar is the X, right, restricted. Okay, so F bar is the F restricted from the global section X to the spec R. Okay, so basically, we're basically saying that the non-zero points intersection with the affine will be the distinguished open set in that affine scheme. Okay. Check out my other videos that I will post the proof below if you're interested. Okay. Okay, so now we have this, right? So simply speaking, we have this power tool. Okay, so let's write down. So what we have, right? We have X, we have P belongs to DBG, and this guy is a spec. This isomorphic to spec BG. Also, less than subset of spec of AF. And okay, so now we are using this theorem, right? Okay, so let's use the previous lemma. So we have XF equals to the XF inter with a spec R. Intersection spec R is a D of F bar. We call the F bar is a XOX restricted to R for F. Sorry, spec R. Okay, so now let's play around with it. So we obviously, right, maybe you think a little bit, you choose the let's see. So I should choose, let's say choose R to AF. And in this case, let's say F to be G, and I call X to be spec B. Okay. Okay, so this tell me that the spec BG, spec BG, let's say we replaced it. Okay, so let's write down. So we got spec BG intersection with a spec R, which is spec AF, is D of G bar, where G bar is G from B to AF. Okay, so this tell me that this guy is a BG, right? DBG. Okay, so DBG intersection with the AF. Right, so don't worry, because DBG is a subset of a spec AF, so this left hand side will be just DBG. And this guy will be the spec of AF, right? We remember in F there's a ring R, right? So and the G bar will be G bar. Okay. Okay, so amazingly, we got a dBg. Oh, sorry. Okay, we did dBg equals d of AF and G bar, right? And G bar is G restricted to from B to AF. Okay, so that means that I can write G bar. So I can write G bar is what? I can write G bar as G prime divided by Fn, right? Okay. So these guys what? These guys are spec of AF restricted and G bar. Okay. So finally, you just need to check. So this is a very simple exercise. You just need to check the spec of AF G bar is spec of A G F G prime. Okay, so this is just very simple. You just check by yourself. So spec AF restricted on G bar, where G bar is G prime divided by Fn. You just play around with it, so you can prove that it's spec of AF G prime. Okay, so if you have this, then this guy will be the spec of AF G prime, and this guy will be D of A of F G prime. So this guy is a distinguished open subset, and this guy is a distinguished open subset simultaneously. Okay, so this is a proof of this Vakil 5.3.1 using the previous Harsel exercise. And then once you have this, then definitely the next video we can prove the affine communication lemma. See you guys next videos.